Now you're going to see what it's all about. So this is something that we don't need to consider now. Okay, so I'm going to come back to some basic properties. Okay, why we introduce moving average process, and what are the major characteristics of them. Okay, but first off, I mean, we basically conclude that the process is stationary. Okay, so no matter what kind of coefficient you got, the process is going to be stationary. That's just a fact. I mean, basically what you have. Okay, now I'm looking at another representation of the process. Okay, so for instance, let's just consider the following example. Suppose that you have a moving average process of order P. Okay, now let's start with the moving average process. So the first order moving average process. So you have constant plus the white noise plus B times epsilon T minus 1. Okay, so here you have that the stochastic process Y is going to be a moving average process of order 1. Okay, so this is going to be a moving average process of order 1. Now, if you remember the lag polynomial, okay, so here, then basically you can summarize this expression, okay, by using the lag polynomial, okay. So this will be basically, and this is what you're going to have here. So I'm going to introduce here the lag polynomial that's called capital B, and I'm going to multiply that by the noise, okay. So, and if the lag polynomial is equal to the following expressions, and then you have 1 plus B times L, then basically what you're going to see is going to be that equal, okay? So all in all, you can say that Yt is going to be equal to the constant plus the lag polynomial, okay, for the white noise, okay, at point T, okay? So lag polynomial times epsilon T. That's going to be the same thing. I'm not sure whether or not you see this, okay? So basic characteristics of the lag polynomial will also give you the characteristics of the process here as well, okay? So that's relatively similar to the autoregressive models as well, okay? And then we're going to put the two together, so that's how we're going to get it, okay? Now, if you have this kind of representation, okay, so let's say we just assume that the constant, okay, so assume that the constant is equal to 0 without loss of generality. Okay, so there is no loss of generality if you assume this. Okay, so without loss of generality. Okay. Basically, we can put it back. So then this becomes, okay, so obviously, so Yt is going to then be equal to the lag polynomial times the white noise. So basically, what you can do is you have 1 over the lag polynomial, okay, times Yt is going to be equal to the noise. Okay, so that's the first thing that we notice here. Okay, so 1 over B of L times the process is going to be equal to the noise. Okay, that's the first thing here to remember. Okay. Now guys, maybe you remember the Taylor series, right? So the formula that I'm using here is basically relates to the following. So this is, I mean, you don't have to use the Taylor series. You can also apply general standard formula for geometric series as well. Okay, so q to the power of j, for j is being equal to 0 to plus infinity, and you take the sum of that, it's going to be equal to 1 over 1 minus q, okay? In case, of course, the absolute value of q is less than 1. Okay, so if the absolute value of q is less than 1. Okay. Now we can apply this, and basically what you would have for the lag polynomial, the following expression. So here I'm going to continue with this part, okay, of this expression. So here you have 1 over the lag polynomial at point L is going to be equal to 1 over 1 plus, and then you have B times L, okay? And if I want to make that similar to this expression, what I use here is the following, okay? So what I use a little trick here, so I may look at it like this. So this is going to be equal to 1 over 1 minus, and I'm going to put in parentheses, negative b times L. Okay, so then it becomes similar to this expression. Okay, so and then what I'm going to use here is I'm going to take that, okay, so that expression to be equal to q, and I'm going to replace that here, this expression with that. So this is going to be equal to, and then you have it here. So the sum that starts is equal to j is equal to 0 to plus infinity of the following expression. So here you have negative b to the power of j times L to the power of j. So negative b to the power of j times L to the power of j is basically what you would get if you use, or you apply the Taylor series here for that as well. Okay, I'm not going to do this because this is something that we don't necessarily need to here for this simple expression. But if you have a higher order moving average process, then basically you would automatically use that. Basically use that representation here for it. So that's not what I'm going to do here. Okay? Is this clear so far? Okay? So by looking at this expression, okay, so this is the first equation that I got, and the second equation is basically as follows. So here you're going to see that, okay, so I'm going to replace this one, okay, by that one, okay, right? Okay, so if I replace these two expressions because they are equal, then I'm going to get the following, and this is what what I have here, okay, is, okay, so, and that's what you're going to get, okay, so basically, the sum, okay, of this expression, so here you have negative b to the power of j times the lag operator to the power of j, okay, where j starts at 0 and it goes until infinity. Okay, so this is going to be that expression. If I multiply that by yt, okay, so if I multiply this expression, okay, by yt, okay, then of course, if you multiply the lag operator to the power of j by yt, then what you're going to get is this is going to be yt minus j, obviously. Okay, so this is how the lag operator is defined, basically. So here you have negative b to the power of j times yt minus j, obviously. That's how the lag operator is defined. And that is equal to the noise. Okay? So this is equal to the noise. Now, of course, if I start at 0, okay? If I start at 0, then of course negative b to the power of 0 is going to be equal to 1. So I'm going to take out the first one. Okay? So what I do is I take out the first one. Okay, so this is going to be equivalent to the following expression. So here you have yt, okay, times, negative b to the power of 0, which is going to be equal to 0. Okay, so then what I do here is plus, and then you have the sum, and now you start at 1 at this time, so not equal to 0. Okay, so here we have 0, right? Be careful, but here we have 1 because I was taking out the first, basically the first summand here from this sum. Okay, so I took it out. So the first summand is going to be yt, of course. Okay, so then I keep the rest as it is. Okay, so then you have here yt minus j, and then this is going to be equal to the noise at point t, obviously. Okay, so again, I started here. I developed, the Taylor series here for this point around 0, and then what I'm doing is I was replacing that expression here for the inverse of the lag polynomial. This is going to be the inverse of the lag polynomial, and here you're gonna and of course this is going to be equal to the noise because that's how we started. Okay, so this is how we started here. So that was equal to the noise. Okay, and then all I'm doing here is I'm taking the first one out. And if I take the first one out, what I'm going to do here is I'm going to put this expression here to left-hand side. From the left-hand side to the right-hand side of the equation. So what you have here is going to be yt, and this is equal to, so you have the negative of the sum, okay, of negative b to the power of j, okay, for j being equal to 1 to plus infinity of yt minus j plus the noise, okay? So I'm taking this whole sum to the right-hand side of the equation, and this is what I'm going to get here. So you have negative the sum, okay, for basically this Dirac operator plus epsilon t, okay? And yeah, so the last thing that I'm going to do here is I'm going to change the sign here as follows. So what you have, and this is what you're going to see, is you have, I will, okay, so I will have a factor -1, and I will multiply that here. So this is going to be equal to -1 to the power of j minus 1. Okay, so the power of j minus 1 of j being equal to 1 and plus infinity, and then I take out negative b to the power of j, so that's going to be the result. Okay? Right? Okay? So basically I'm negative b to the power of j times -1. Okay? So you can take that also to the power of j. This is going to be equal to this, so this is going to simplify. So that's kind of how you're going to get basically the sign of this coefficient here. Okay? So if, let's say, j is odd, then it's going to be positive, and if j is even, then it's going to be negative, obviously. Okay, so if j is odd, it's going to be positive, and if j is even, it's going to be negative. That's what I'm using here. Okay, so
do you still have power on b?
no, but the b to the power of j, yes. So you have j here, but you can take out the coefficient here, which is going to be negative. Okay. So I mean, of course, guys, this is I think you might struggle here. So you have negative, and here so minus negative b to the power of j is basically equal to -1 times -1 to the power of j times b to the power of j. So that's where it's coming from. Okay. So then you would get the same thing if you multiply two powers, then you're going to get, what you're going to get is you have to add the exponents. Now if you add the exponents, you're going to get the same thing here. Okay? Because all that matters is basically if the exponent is even or odd. So that's the only thing that matters. So here you're going to also you could have a j plus 1. Okay, so that's not important. Okay? So this is something that you could have there. Okay? But you don't have to. Alright? Okay, now what you see here is basically this is an autoregressive, okay, so this is an autoregressive process of order plus infinity, right? Because here you have the coefficients, okay, so these are the coefficients, right, of the process, okay, and this is an autoregressive process of order infinity. So, and of course a stationary, okay, which is stationary, okay, so which is stationary. Right? So a first order moving average process is basically an autoregressive process of order infinity, which is stationary. That's, this is maybe just, a special case of that. Okay? Later you're going to see what's the use of that, but this is just a Racine property. Okay? So, and of course you have to be careful because this sum, okay, is only finite if, let's say, the absolute value of b is less than 1. Okay? So, this is an autoregressive process of order infinity, which is stationary. Okay? And in case of that, the coefficient here b has an absolute value which is strictly less than 1. Because if that's not the case, okay, then basically the process is not going to be stationary. Okay? Right? Okay? Good. Now, of course, I assume that the constant was equal to 0, but it doesn't make any difference. Okay, so the difference is not much. Okay, so basically, all right, so that was summarized by the next proposition. So I will summarize that result. Okay, so basically what you have here is that, okay, so the lemma that I'm applying here is that basically if y is a moving average process of order 1, okay, and we also have that the constant is equal to 0, okay, then basically what you can get is yt, and this is going to be the same thing, okay. So here you have infinite sum. So here you have an infinite sum of -1 to the power of j minus 1 times b, okay, times epsilon t minus j plus epsilon t. Okay, so basically what you have here is that, okay, so y is also an autoregressive process of order infinity. Okay? Right? And this has to be stationary, guys. Okay? And stationary conditions for autoregressive process of order infinity only hold if the corresponding coefficients here for the process, okay, has an absolute value which is less than 1, because if that's not the case, then the process is not going to be stationary. So then the representation is not finite. Okay? Because the sum which I was using here from the geometric series will not determinate. Okay, so that thing only works if the absolute value of the sum is of the absolute value of the coefficient is less than 1. Okay, so that's going to be the same thing. Okay, so if you have a moving average process of order 1, okay, and basically the constant is 0 without loss of generality, then you can express basically the process as an autoregressive process of order infinity, provided that basically that the absolute value of the coefficient here is less than 1, because in the other case the process is not stationary. Okay, and now finally I want to introduce you to the mixed models. Okay, so the mixed models, this will be, and this is going to be the next definition. Okay, so for what you have is here in this case, you have a stochastic process. This is going to be the autoregressive process, or you have an autoregressive moving average process. Okay, and then you call this orma. Okay, now here of course you have two orders. Okay, so P refers to the lag length of the autoregression part, okay? And Q refers to the lag length of the white noise, okay? You understand? So you say the ORMA process, right? So you say autoregressive process of order P and Q, okay? So this is what it means. So autoregressive, toe-regressive, moving average process of order P and Q. Okay? So where of course P refers to the lag length of the autoregression part, and the number Q refers to the lag length of the moving average part. Okay, so again, P refers to the lag length of the autoregressive part, and Q refers to the lag length of the moving average part. So basically, the process will look like this. Okay, so here you have yt, and this is going to be equal to, and here in this case you have the constant. Okay, so then plus a1 times yt minus 1. Okay, then plus a2, times yt minus 2, okay, then plus, okay, so then this goes on, so then you have ap times yt minus p, so this is the autoregressive part, okay, And then what you have is the moving average part. Okay, so then plus, alright, so then you have the noises. Okay, so then white noise at point T. Okay, so then you have P1 times the white noise at point T minus 1. Okay, so then, and so forth. Okay, so then you have the last one is going to be, here you have a slope of BQ times the white noise at point T minus Q. Okay, so this is how the process will look like. Okay, so you have an autoregressive part, which is in the first line, and the moving average part, which is in the second line, obviously. Okay, now of course these are the parameters. Okay, and of course you have to, you have to recognize here that the past, okay, so the past realizations of the autoregressive process do not correlate with the current realizations of the white noise. Okay? Alright, so basically what you have to have, you have the usual part. Okay, so the white noise has the variance sigma squared and the expectation is 0, but you need to consider that the covariance, okay, of the current observation of the noise does not correlate with the past observation of the process. Okay, so here let's say you have yt minus h, and so this is equal to 0 if, let's say, h is greater than 0. Okay, so again, the current observation of the noise does not correlate with the past of the process y, and now this is not true the other way around. Okay, because here basically the past of the noise, you have that in the process. Okay, so you have the past realizations of the noise, but the current observation of the noise doesn't correlate with the past of the ARMA process. Okay, so the autoregressive moving average process, which I refer to as ARMA process or ARMA model. Okay, does it make sense? Okay, right? And that is not true, of course, the other way around. So the current observations of the process do correlate with the past of the noise. Okay, because you have the past here and there. That's obvious. Okay, so basically this is what you're going to do. All right, now of course if you want to express this by means of Lac polynomials, okay, so I'm going to use this as an example, then it's going to be obvious what you have. Okay, so basically, this is what you can do here is this is much more compact notation here. So here you have the Lac polynomial times the stochastic process, which is an ARMA model, is equal to the constant times the Lac polynomial of the noise. Okay, so here you have the Lac polynomial of the noise, and here you have the Lac polynomial of the autoregressive part, basically. Okay, so this is the same representation. Okay, so if y is an ARMA model, okay, of order p and q, then you can use that notation here, which is a little bit more compact, let's say. Okay, so where the Lac polynomial of the autoregressive part is as we have considered, so this is going to be 1 minus a1 times l to the power of 1 minus a2 times l to the power of 2 minus and so forth. Okay, so then we have minus ap times l to the power of p. Okay, so this is the Lac polynomial of the autoregressive part, and you also have the Lac polynomial of the moving average part, and the Lac polynomial of the moving average part is going to be equal to 1 plus b1 times l to the power of 1 plus b2 times l to the power of 2, okay, and so forth. And the last one is obviously bq times lq, l to the power of q. That's going to be the last one, okay? So this is going to be the Lac polynomial that you have here. Okay. Now, as far as stationarity conditions is concerned, the moving average part is stationary, always. Okay, so no matter what, the moving average part is always stationary. So the process, the ARMA process, is stationary if and only if the autoregressive part is stationary, obviously. Okay, so the process, right, is stationary. Okay. if and only if the autoregressive part, okay, part is stationary, okay, right? So that's going to be it. Now, what were the conditions that the autoregressive part is stationary? The autoregressive part is stationary if and only if the lag polynomial of the autoregressive part has roots which have an absolute value that is greater than 1. Remember that? Okay, so if the roots of the lag polynomial have an absolute value which are greater than 1, then of course the process will be stationary. Okay, so what does it mean? Okay, so basically it means, okay, so that the roots, okay, so that, okay, so if, let's say, if you collect the roots of the lag polynomial, then you would get that the absolute value of the roots are always greater than 1. Okay, so please note that here the roots can be complex numbers here as well. Okay, so that's just going to be it. Okay, this is the first thing which is equivalent. So the process is stationary if the roots have an absolute value that are greater than 1, or the other way around, if the roots have an absolute value that is greater than 1 of the lag polynomial, then the process will be stationary, because our model is stationary if the autoregressive part is stationary, so you don't need to focus on the moving average part. Okay? Or this is the other condition that we developed. Okay, so basically we have that 1 over the lag polynomial of the autoregressive part is finite. Okay, and this is finite. Okay, if and only if basically it can be expressed as follows. Okay, so this is finite. Okay, i.e., so this means that basically that this can be expressed, okay, by using the Taylor expansion. Okay, so you would get basically that here you have j is equal to 0 and plus infinity here for the sum, and here you have some coefficients. So a alpha j times L to the power of j. So alpha is our some coefficients. Okay. So for the first order autoregressive part, it's clear how this coefficient will look. Okay, but these coefficients here, so I'm talking about these. Okay, depend on the lag order of basically the order of the autoregressive part. So you can extract them from the autoregressive part, of course. But it's not clear. I mean, in general terms, how you would basically you would get these. Okay, so there is no general expression, you know, that covers all cases in terms of the autoregressive processes. So you have to calculate them by your own, but it doesn't matter. So basically, it states that there is a possibility for that. Okay? Now, and these coefficients, but satisfy that they're absolutely summable, but I will not add this here to this condition. We already considered that. Okay, so here basically the autoregressive part will determine whether or not the corresponding process is stationary. Okay? And this is what we consider. Okay, guys. Now I think I'm going to stop here. Okay? I will upload the lecture notes. Okay? And then you're also going to get the examples. And probably by the end of this week, I will release the second assignment. Okay? Which will be about the autoregressive processes, and you probably need to implement something. Okay? So just prepare for that. I will tell you what to implement. Okay? So then you're going to get, let's say, 2 weeks for that. Alright? And then you have to submit a program. Okay? So because we also want to do some practical stuff as well. Okay? So I will tell you exactly what to submit. Okay? Don't worry. Okay, guys, so that was it. Okay? See you next week. Yeah. So, Das ist aber egal, das ist beides dasselbe. Also jedenfalls ist der Erwartungswert der Erwartungswert ist ja, also der Erwartungswert im Produkt ist die Programmierung. Das ist so, aber vielleicht habe ich mich da einfach nicht geschickt.
Politik mit der Geschichte.
Also hier, ne? Ich hab's gefunden. Das ist ja das Gleiche.